hope the sound is okay. If someone has already joined and can tell me in the chat if all works. I need to stop it from my browser because I have the echo, but that also means that it works. So I think it was a week ago I started to look at, let me share my screen. I started to look at the USD Index website from Marcus Winant. Marcus has written a book about the right usage of SQL and especially indexes. And most of the points are free in his website. And most of examples that we find in this website, sorry, most of the examples are, looking at example schema, most of the examples are for multiple databases like DB2, MySQL, Oracle, Postgres, SQL Server, SQLite, even SQL Base. Yeah. So here my goal is to run the Postgres one on YugabyteDB because YugabyteDB is Postgres compatible. We use the Postgres query layer, so most of the SQL that we find in those examples should work on YugabyteDB, but the internals of indexes are different because YugabyteDB is a distributed database, and then this needs a different implementation. I started to talk about it in the last episode. Basically, Postgres uses heap tables, B-tree indexes, and B-tree are efficient because there is a shared buffer shared by all the sessions on one node, but that works only because all the sessions connect to the same node. In YugabyteDB, you have multiple nodes, can be 3, can be hundreds, can be 1,000, and you can connect to any node, see the whole database, but the data is distributed everywhere, the indexes as well, and then you cannot have a common shared buffer. You cannot work on buffer, you work on rows, on tuples, and read and write operations that are distributed everywhere. So the internals are different, which means that the performance may be different. Reading the execution plan may look the same, but doing a bit different things, and that's the goal, doing that. So I did about 1 hour last week. It is still available on Twitch, and it is also available on my YouTube channel. So if you go there where I put videos, the last one is this one. I will put this one because I'm currently recording there. I will do no more than 1 hour because I have to go to an AWS meetup. AWS is opening a new region in Switzerland, and is doing a meetup about that. Physical meetups are possible now. So on your YouTube, of course, you have also all my references, email. I'm a lot on Twitter. I'm on LinkedIn, of course. And you can find also interesting stuff in the Yugabyte YouTube. For example, at Yugabyte, we do a short talk every week on Friday, and it's called the YugabyteDB Friday Tech Talks. And I did a small episode on indexes, and I will do another one. Oh, sorry. Too many advertisements on YouTube. But I did already one on indexes 2 weeks ago, and the next one you can find it on LinkedIn. So we do a lot of things at Yugabyte, but next Friday This is the one where I will talk about partial indexes and expression-based indexes, which is basically, I think, what I will see in today's chapter that I will look on USD Index look. Okay, enough talking. Let me check what I have in my on my database. The last time we were at this query. So if you remember, or if you look before at the first episode, this was about concatenated indexes, where we started with an employee tables, and then the idea was like merging multiple companies and then adding to the employee ID the need to add the subsidiary ID, because in the different companies you may have employee number 1 and then you need to identify them uniquely. And the idea there was to show that with an index, let me show the structure of my employee table. So simple table, only one index, which is the primary key, starting with the subsidiary ID. I've no more indexes, which means that in Postgres, this is one IP table and one index. In Yugabyte, this is just one table, which is the index, which is the primary key. We store the all the table column values within the primary key. And then a query like this one, looking, I can run it maybe to show the values. Whoops, was not in the right pen. Yeah, so showing the first name and the last name, but only for subsidiary 20. And this can use the index. It's an index range scan because the index is sorted on its columns. In YugabyteDB, before being sorted, it is hashed. But I query for only one value of subsidiary ID, which is only one hash value, which goes to only one tablet then. And in this tablet, we are sorted by the hash code of subsidiary ID, by the subsidiary ID, but it's all the same, the one that we are looking for, and by employee ID. So this is a range scan going directly to one tablet. I may show the number of tablets that I have here if I go to let me open, sorry, a new pane, maybe. I think this is my lab where I can see my employees table. So that's the primary key, and I have 3 tablets there, but only one is read. And what I did the last time also was running a function of mine where I reset the statistics before I execute my query and then check the statistics, and then I can see that only one tablet is read there with a certain number of 6 into the index and reading the next value. And this tablet has its leader in this node, and I can check that. Which one was it? Tablet before something. This is funny because I don't see. Oh no, this is the table ID. 63, the leader is there, so this is the tablet we were reading from. I displayed the ID of the. I don't know exactly which ID I'm displaying there, but this is not the tablet ID, but I can see it from from the leader. I'm just checking that I have no indexes because it is the primary key. We'll have to check my script to see exactly which ID. I'm sure that, but that's not a problem. So this is a range scan and this is fast. And now let's look at the USD Index page about this. To go further, in the previous episode also, I mentioned that in Postgres, you may see some bitmap index scan because reading from a primary key index to a heap table, many rows can be very inefficient because each entry has to read a row that can be in any place in the table. And then Postgres has to optimize that and optimize that with a bitmap, reading many entries of the index, doing a bitmap of the blocks that need to be read to get the rows, and then going to those blocks only once and in the right order to be efficient. We do not have heap tables. We have directly the values in the index, so we do not need this kind of plan, and our plan is more efficient when reading from the primary key or when doing an index-only scan on a secondary key. So this is the explanation. In other databases, you still see that you read, so Oracle also has heap tables, so you see this differently, but you see an index range scan then going to the table. I think this is an old version. More recent version should do some kind of batching there. MySQL is storing the whole table in the primary key like we do with YugabyteDB. So that's only one operation. DB2 has two operations, index and fetching from the table. SQL Server, you can choose. It seems that here you have an index and then a lookup to the table. Yeah. We are interested by Postgres and how it is different in Yugabyte. So this plan is different in Yugabyte, but this is the most efficient access we can do. An index scan on the primary key is like an index-only scan. It doesn't show us an index-only scan here because we use the same semantic in the query planner, the same semantic as Postgres. But from here, you know that you read only one tablet, which is the table actually. Okay. So this was about concatenated index. My index is on multiple column. I can recall the describe of the table. This is a concatenated index, but it can be used with conditions on the first column. So that's the idea. You don't need an index on subsidiary ID alone if you have one that starts with subsidiary ID. The goal in any database is to reduce the number of indexes. So the goal is not to have one index that fit each query. The goal is to have a limited set of indexes which covers all your queries or all your critical queries, at least the queries that need to access to predictable with predictable performance to a certain number of rows. The other can do a sequential scan if it's reporting, but you need indexes for DOLTP access, basically, and you need a reduced set. So no need to define an index on subsidiary ID only here. That's the main point. And this is the point that is made here. I can put that a bit larger if you want. So this is the point that is made by Marcus Winant there. In general, database can use a concatenated index when searching with the leftmost columns. An index with 3 columns can be used when searching for the first column or for the first 2 columns or searching for all columns. We are here in the chapter on the where clause. We will see that indexes are also used to optimize group by, order by, and other operation. Here we are on optimizing the where clause, selecting a subset of the rows. Even though the two index solution deliver a very good select performance, the single index solution is preferable because it saves storage. Of course, if you really don't need the second column, an index on only one column will be smaller, and smaller means it's not safe disk, but smaller means that you can also fit more information in cache and then can be faster. And it helps also the overhead of maintaining a second index. But this is the main point. The fewer indexes a table has, the better the insert, delete, and update performance. And I will add also maintenance, even if we can create and drop indexes online without stopping the application. Those operations take time. So that's the main point. To define an optimal index, so it's not an optimal index for one query, it's to define the optimal set of indexes for your set of application access queries. You must understand how indexes work, and this is where YugabyteDB may be different, may work differently than Postgres ones internally because there are different structures. You must also know how the application queries the data, so this is mandatory. In the past, and I mean in 10 or 20 years ago, we used to do at least a logical data model before looking at the queries. Just looking at the data. You remember the business analysts sit with the users and defined the data. What is an order, what is a product, what is an employee, what is a department, and build a static model, an ERD or UML class diagram of it before thinking about the access, and then going to the physical model, defining the keys, defining the indexes for the access. Today, we do not do that because we do not spend months to do this design. Today, we have a use case, microservice, and we want a database for it, and we need to look at the access pattern for it and design directly for it. That doesn't mean that we cannot add more use cases later. Of course we can, because SQL has this agility to add more column, to refactor, to add more indexes, but you need to understand how you will access to the data. So basically, you should know the shape of your queries and what you will find in the where clause. If I have tables with orders, customers, products, I should know if I navigate from one product to all orders for this product or to all orders from the last week for those products. This is the kind of thing. Let's go further to the next page to see more technical things. So we add an employee primary key to improve the performance of all queries that search by subsidiary only, and can be used for all queries that search by subsidiary ID, whether there is additional criteria or not. We'll not go into the query optimizer, which is called query planner for Postgres, and YugabyteDB, we use the same terms. So here is a query, and I will run it, and we will see what we can say about it there. So this retrieves one employee by subsidiary and last name. If I will do the same as before, execution plan plus statistics. So this is interesting because I have an index, the primary key. The index has subsidiary, has the employee number, but I don't really care about the employee number here because I'm searching by the name, the last name. So the index can still be used. That was the point. Can still be used to filter on subsidiary. And I can see that it was used for this predicate because the index condition on subsidiary is there. But I have other criteria on last name. But this one cannot be done by the index access. It is done afterwards, and this is why it is mentioned as filter. So if we look at the numbers, because when I run an explain analyze, I didn't show the cost to fit on the window, but I have the actual time. That's one thing, but more important, the actual number of rows. My query returns one row because I have only one employee with last name WinHand in subsidiary ID 30. However, in subsidiary ID 30, I have many employees. How many were read there? I can know that from this value. So after applying index condition and filter, the result was one row. But this addition information tells me that the filtering removed 999 rows, which means that the output from the index, we don't see that directly, but the output from the index was 999 plus the one that was not removed by the filter. So 1000 rows from 1000 employees in subsidiary ID. And the index access was fast for those one, but then it had to be filtered. Let me first check that those are the real numbers. When you have small data, you can always verify the numbers to be sure that you understand them. I will select the subsidiary ID and count for all of them from employees group by subsidiary ID, order by the group by. Okay, I have a lot of subsidiaries. I expect, 1000 for subsidiary 30. So the number match. And before more explanation, let's look at the additional statistics that we don't have, at least yet, in the execution plan in Yugabyte, but that I check with my little function that looks at the many metrics that are exposed to a JSON endpoint. So this is a range scan, and there's something I didn't expect. Yes, this is a range scan on the table that is the primary key. So there is no secondary index. So only one tablet because I'm hashed on subsidiary ID. So one subsidiary ID is only in one place, and many six there we see 2 times 1000, which is what is behind those 1000 of index entries that have been read. So that's a lot of work, especially in a distributed SQL database like YugabyteDB, because those 1000 of rows had to be fetched from this node to the node where the query is processed. I think I can see it as show listen addresses. Yeah, I'm connected to the node 61, but I'm reading data that is in node 63, which means that 1,000 of rows have been read from the index from this place going to this node, and this node is the row removed by filtering. So you can understand the performance problem you can have, and that depends on the distance between the different nodes. Of course, if you are in the same availability zone, just a matter of milliseconds. But if you have geo-partition and you are in multiple regions, you probably want most of the filtering happening within the index at the storage layer. Okay, so of course we have solutions to optimize that. I will see what is mentioned in the Marcus Winand page, but basically you can see that in the explain plan, I also use verbose, which gives me the columns that I need for my query. So in addition to the one in the index, subsidiary ID, I need the phone number, I need the last name, I need the first name. If I put all those columns in the index at the end, or at least I need to leave the subsidiary ID in front to be able to do the range scan. But if I put all the other columns after this one, then I may get everything from the index. That's general also for secondary indexes. But here we are on the primary key. So we do not have additional hops to the table. We have already all columns. Then the question is why this was not filtered directly from the index. And actually, I don't know exactly in this case the reason for it, because it's a primary key. Yeah, there are some reasons. If it was in the primary key itself, in the columns itself, or in the index column of the index, it could have been filtered from there. But here, the thing is that in YugabyteDB, we have those two layers, the SQL processing layer, that is Postgres, and the storage layer. And for the moment, in the storage layer, there is no Postgres code. So depending on the data types, there are things that look simple, but where we may need the Postgres code to do the filtering. If you have some things that are specific to data type, to collation, this requires more code than just an equality between two character strings. So that's probably the reason. Let's see the optimizations mentioned in USD Index Luke, and we will see if they fit, if the optimization for Postgres fit to Yugabyte, or if we have to do something differently for Yugabyte. So we were there. This is a plan in Oracle, but same idea as in Postgres. It's an index range scan, and you can see a similarity. What is index condition? The access to the index in Oracle is called access, and what is the filtering afterwards in the output from the index is called filter in Oracle. Oracle has, doesn't tell you the number of rows that has been filtered later. So, just reading, started with employee, part of the where clause. Yeah, so another thing that is very important when you want to understand how index work, sometimes you think that an index is good, but it's not chosen by the query planner, and then you want to see how it behaves with something that the query planner doesn't choose, and this is where we use hints. So we have hints in YugabyteDB. They are not there by default in Postgres, but we enable them by default in YugabyteDB, and we will do the same. So this is a no vehicle syntax, but I will do the same. Basically, what Marcus is doing there is showing what happens if we do a full scan. So I will copy the role and add an int to it. I'm copying the role so that we also check the statistics. So I want to force a sequential scan, that's the name of the full table scan in Postgres and then in YugabyteDB for employees. So quick reminder about the previous plan and now the new one. And I will increase the screen because it can be interesting to see both of them. Oh, I have a syntax error in my int. This usually happens when I talk while waiting sec scan. Yeah, so here it is. So there I just say do not use this index. The index was okay, but just checking, do not use this index and do a sequential scan on the table, which is the same structure in Yugabyte as the primary key, except that in this case, I doesn't query on a range. I query all rows, and all rows are filtered later by the SQL processing layer, by the Postgres layer. And there we see the difference. I'm reading from the three tablets. So I'm reading all rows for all subsidiaries. You see no condition, no index condition subsidiary, and then they are filtered later. So this is probably not more efficient. With a sequential scan, you don't see a lot of seek operation, many next, because you just read the next value. The time, we can check it, but the time is not really relevant here with small tables. Just looking by curiosity, I had 11 seconds for this one, and sequential scan is a bit higher. Yeah. More rows to transfer between nodes, of course, takes longer. You have a latency. And here in this lab, I have all nodes within the same VM, so not really network dependent. It can be worse with the network. So what was the point looking at the sequential scan? In this case, so this case was a vehicle with heap table. In this case, even if it must read and process the entire table, it seems to be faster than using the index. The index seems to be slow, but this is specific to databases that have a primary index and heap tables. So we are not in this case. I'm just reading it. In this case, best to go through each step of the troublesome execution plan. First step is index one scan. And then the idea with heap tables is to cover, to add the last name in the index so that those thousands of rows can be filtered out before going to the table. We don't have exactly the same case, but we will do it. I will do it. I suppose it's done in the next pages, but I will do it now to show you how it works on Yugabyte. I have a table with a primary key. I will not redefine the primary key. What I will do is creating a new index. So let's check the structure. I will call it employee. So I will index on subsidiary ID because I want to start with it. So subsidiary and last name. So this will be an index that can filter directly on subsidiary and last name from the index and employees. And I will define the same. But adding last name. I will add it first, or maybe I don't even need employee ID for this one. Last name. The defaults are hash for the first one and as for ascending for range for the second one, but I put them so that everything is clear. So creating this index, I will see if it is used by my query. If not, I will use a hint. So this is why I copy it. So yes, it is used. I should have defined a smaller name because it takes the whole screen there. Or maybe I can just decrease the size of fonts. I think it is still readable. And running that again. Okay. I will rename my index. I don't like this long name. Amp sub and last name. So here it is. Here I've created a secondary index, which is able to filter on all my condition. I can see the name of my index. I can see the index condition on subsidiary and employee name. But then it has to get more columns from the table. It's not a primary key index which has all the columns. It's a secondary index. Then I have up to the table to get the last name, for example, and the phone number. So here we have something similar to Postgres or Oracle with heap tables, except that we do not reference in the heap table by a physical location. We reference it by the primary key. Secondary index holds the index column plus the primary key to go to the table afterwards. So we read from more places, but we read less rows because from the index, because we can filter everything from there, we have only one row coming from there. So we go at one place there. We just read the next value, which is the primary key to go to the table. And then we go to the table and we read the 4 columns that we need. So this is efficient. We can make it even more efficient by adding all columns into the index. I will show it if you want, but this is efficient. And here we are on something that is different than Postgres or Oracle. And in a distributed database, we, for the critical use cases, we want to avoid reading from multiple shards for two reasons. First, there is a latency, and also because we ensure consistency. All indexes are consistent. It's not a NoSQL database like Cassandra. Here, everything is consistent. And then ensuring consistency between multiple nodes requires a bit more work. I will do it. We will see what is in the Marcus Winand example later. But for example, in this index, if I add all the columns I need in the output, so first name are already, no, first name I don't have it, so I will add it. And yeah, I will add it there. So first name, ascending also, we will see that later. Last name is already there, subsidiary ID is already there, and the phone number. I will drop the previous index. In production, it's probably better to create the new one and drop the old one afterwards, so that you don't have this time between the two of them with no index. So here I expect an index-only access in index-only scan, yeah. And the difference is that I read only from the index. So the optimal access is either reading only the primary key with index scan, or reading only the secondary index with index-only scan, at least for most of the critical queries. And this requires concatenated indexes where you add more columns into the index. In Postgres, this, even when you see in Postgres index-only scan, this still has to go to the table to look at the visibility of the transaction for the isolation between the transaction. And Postgres tells you how many blocks from the heap table are read. In Yugabyte, we don't have this access to the heap table. We don't need it. We have all the visibility into the access. So heap fetches will always be 0. This is displayed when we put verbose, I think, or only analyze, I don't know. But yeah, not really helpful to read that in YugabyteDB, because this is always 0. We don't have to go to a heap table later. So this is the best optimization we can do for a query that queries on a subsidiary and last name and need phone number and first name. Something else that I will do, and I'm going to different places at the same time, but it's interesting. Imagine that I want all names in the alphabetical order, all names higher than win and. And I can see that this is still okay, still use it the same. And this is because my definition of the index that is there, this is because the last name is ascending. If it was hash, let's put it for example, just to show you. If it was hashed, and in Yugabyte, the way to put the hash function on 2 colons is something like this, if I'm not wrong. So before we were hashed on subsidiary and then ascending on last name. Now I'm hashed on subsidiary and last name. And the query with equal name still works because with a hash value, you can verify the equality because if two columns are equal, the hash of the two columns is equal. However, my other query with an inequality there cannot do the range, the inequality on something that is not by range but by hash, and then the equality on subsidiary is possible but not for this second column, and this is where you see rows removed by filter after that. So I get back to the original index where subsidiary was hash. It's important when you define the primary key and the index keys, it's important to know if you will have range queries, inequalities, or only equality. It's easier with hash because it's easy to distribute on a hash value. With a range, you need to define the ranges, so it can be done automatically by looking at data, but that's more complicated. So the default is hash on the first column. For example, in this case, I do not expect range queries on subsidiary ID. I do not expect a query reading subsidiary between number 30 and 33, for example, because those are ID generated. They do not have a real order in their business meaning. Last name is different. Last name has an alphabetical order, and you can expect people doing queries like, oh, the name starts by those letters. Okay, I will just check where we are to synchronize with this page from USD Index. Look, because I went further because the indexes are different. So Marcus had another example with an index only on last name, which has fast access for the last name, but then not for the subsidiary. I can create one like it just to show you. Index only on last name. I define it as ascending because I know that on last name people will want something ordered. And running the same query there, probably this index will not be used, or yes, it is used, yeah, because last name is quite selective. So this index is used, but used only for the condition on last name. The guess there is that the last name is selective enough. Maybe it will get multiple rows from different. You can have the same last name in the same subsidiary or in different subsidiaries, so maybe it can get multiple rows, but the filtering is done later on the subsidiary. Here, it's not an index-only scan because it's a secondary index where I don't have all the output columns in the index, and then it reads, but it reads only one entry. This is the most important. From the index, I read only one entry because this entry read from the index from this node goes back to the node where I'm connected to, where the Postgres executor will read the index entry and send the requests to the table nodes. So the most important is that from the index, you return a small number of rows, and small means what? Small compared to the result that you want. Of course, if the result of your query is thousands of rows, there are some points where thousands of rows should come out from an index. But if the result is one row, you do not, you expect just a few rows coming from the index, not to filter them at the end. Filter early. That's the goal of the indexes. Okay, what do we have there? Yeah. I think we have seen most of all from this page. I will just start on this because I mentioned that I will do 1 hour only. So I will start on this page. This page is on functions. So that's quite useful because we have seen that we can index columns, but what we index is our search key, and the search key may be different from the column that is stored. Let me just put the link in my file so that next time I know where we are. Next time, maybe next week. I don't know, Tuesday or Wednesday, when I will be available. I think it will be Wednesday because on next Tuesday I'm presenting at a Kubernetes meetup in Geneva. So we will start with this one and we'll see the rest. So first, this can be called index on expression or function-based index. Yeah, depending on the database. Let's check. DB2 supports it, but only recent versions, and not for user-defined function. That's quite amazing to see. This old database not supporting everything there. Oracle has function-based index since version 8a, so, and called that function-based index just because you index on a function. Postgres calls that index on expression, which is probably better naming because it's not only a function. If I concatenate 2 columns without defining a function, it's still an expression, and SQL Server has it. And then Marcus has 3 examples for them. One very common one, upper and lower. Yeah, we have seen a search on a name where the name is put in uppercase. And maybe you store all names in uppercase or maybe not. So usually people want to do a case-insensitive search, and this is the next example there. So let's run directly the query mentioned there by Marcus. I'm not really interested by the results because I know it. I can run it if we want. Whoops. I'm lost in my copy pasting. Yeah. I know that I have only 1 row, but I'm interested by the execution plan and the statistics to be sure that I know exactly what I read from where and how much. So here it is. This is a sequential scan, reading the whole rows from all tablets and filtering them later. When you see this filter and rows removed by filter, you know that you had to fetch rows from many places into the place where you are connected, and this has a cost. What I would like is an index where I can see this as an index condition. I have an index on employee last name, but I need an index on upper employee last name. And this is kind of thing that we can create with function-based indexes. So here Marcus is mentioning that this is sequential scan in all databases without the right index. And he mentions that even if for us it looks obvious that we can use the index, basically it can be any function. So the query planner doesn't know exactly what it is. And the cardinality is also different. We need an index where we can go directly to a place from the binary value of the search key. So with upper, it can be many places. So we need to index on it. So this is what is indexed with that. Let me put it there first. And I will immediately change the syntax. I think this works when a function, but generally, the general case for expression, you need to add more parentheses. So it works with a function, but with an expression, you need the parentheses. So best to put them. And I create this index and we'll run exactly the same query as before. And I can see that, so for people coming from NoSQL, they are not used to this intelligence of the optimizer. For the moment, I used a hint to force an index only when I wanted to see something specific. But for the moment, the query planner is choosing the right index. Even if in Yugabyte, in the current version, I'm on version 2.12, select version 2.13. Oh, I have an old version there. Yeah, production, but no problem. Yeah, for the moment, we have a very limited cardinality estimation because we are using the query planner from Postgres, but there are more things to put in the estimation when it comes from distributed nodes. So here, but I will stop there and we will go into it on the next episode next week. But here I can see that just by creating an index on an expression, a function, anything that is in my query, I can use this index to go directly to the rows which have renamed as an uppercase. And here I have it directly, of course. It's not an index only just because I don't have all columns there, but I could add them. But from the index, I read only one row there because I have only one. And you see no additional filtering. You see no rows removed by filters. This is very efficient. So this is for secondary indexes. You do not put expression in the primary key index because the primary key is about the columns of the table, but for secondary index, you can do that. And so that's also a way to have fast access, even if you use functions around columns. Always very important to look at the execution plan, because without the execution plan, you don't really know if the query planner will be able to use an index or not. Using execution plan, you can see if it's used, and if it's not used, you can also force it with hints to understand why it is used or not. Okay, so just bookmarking. We have started a function. We will see the next one next week. And don't forget, if you want more about indexes, this is Friday, so before the next episode of this Twitch, and this is on the Yugabyte LinkedIn. I will do the same expression-based indexes, same idea, and also mention partial indexes that we have not seen yet in this Twitch, but that we will see in the YFTT. Thank you very much. Do not hesitate to contact me. Twitter is the best, but I have also blog, email. I will put the recording on YouTube. The recording stays on Twitch, I think, for 1 or 2 weeks, but then I will put it on YouTube, and see you later. Thank you.